One of the most important applications of integration is that it is used to calculate the area under a curve. In the last video we looked at definite integrals, and in this video we're going to use that skill to calculate areas. Before we get into that, we're going to look at why and where the notation comes from. In the first example, I've got the equation y equals 2x and I've drawn a line at x equals 3, and we want to find the area under this curve. Now, when the line is a straight line, it's a lot simpler to use basic geometry than any fancy math techniques. We've just got a right angled triangle here where it goes between 0 and 3, so our base will be 3. The height will be just 2 times 3, so 6. That's 3. So our area will be half base times height, which is 9 units squared. Now, of course, it's not going to be as simple as a straight line. Instead, you're going to get something that's more like a curve. And say I want to calculate the area of a curve shape between value A and B. Because it's curved, it's a lot harder to find its area. And so instead of just trying to find one area, I'm going to split this up into a number of different shapes. And those shapes will be easy to find the areas of, and then I'm going to add them together. The easiest shape to find the area of is a rectangle. And so I'm going to split this up into a series of equal width rectangles where the height is the value of the function. So I'm going to go up to the function, cross by 1 and down. Then I'm going to keep drawing these rectangles until I reach the end. Up to the function, across, down, up, across, down, up, across, down. And I'm going to do this until I reach B. Now, you may have noticed that at the start the rectangles were overestimating the area, but by the end they were quite considerably underestimating it. And so we're going to look soon at a way to minimize this error. But first, the value of each of the heights of these rectangles is just the function, because it's the y value, so fx. And I'm going to say that the x value along the bottom is just some sort of step in x. A common symbol to use for a step in x or a change in x is just delta x. And so the first area will just be the function, and if we just call this x1, and the next one will be x2 and x3 and so on, is the function at x1 times by that change in x. That's the first area. Then the function at x2 times by the change in x, and then that will go on until the end. A way to write a repeating sum is to use sum notation, which has the capital letter sigma of the function at, and because the 1 is then becoming 2, then 3, I'm just going to use letter I times that change in x, and this is going to go from I equals 1 to the end. So in this case we've got x1, 2, 3, 4, 5, 6, 7, and so I'm going to do until 7. Now, in order to make this more accurate, one method is to make the size of the rectangles smaller. Now, if you were to make them really small, then we're going to minimize the area. I'm just going to make the rectangles half as big, and let's just see what it does then. So there's half, and across, and then across, and across. Now the steeper the curve gets, the more this is going to cause an error. But if we compare these rectangles to the earlier ones, I'm hoping you might be able to see that the amount of error is a lot less. Now we're going to keep making the width of these rectangles smaller and smaller and smaller until the error is so tiny. Now the way that we write that in maths is we're changing that capital delta, which is the triangle, change in x, to a smaller symbol. Now, a small change in x in calculus is denoted using the dx symbol. They still have the function of x as the height. The reason that it's used as a little d is that, well, delta capital is that, lowercase delta looks something like that, which sort of gets rewritten as a d. When we're refining this, we're making it a smoother and smoother function because we're getting less chunky, and so we're going to change that sum notation to an elongated s, which looks like that. It's almost like a smoother sigma function, and we're going to times our heights, f of x, by our bases, and we get the integration sign. We're going to do that between a and b, which is a and b, and we end up with what was the definite integral. And so now we can see that the definite integral is calculating the area between the curve and the x-axis. To see this in action, we're going to calculate the area between the curve y equals x squared minus 2x plus 4 and the x-axis between x equals 1 and x equals 3. So to find the area, we're just going to integrate between 1 and 3 of our function x squared minus 2x plus 4 dx. And now we know that the dx is the base of these rectangles and the function is the height. Gives x cubed over 3 minus x squared plus 4x between 3 and 1, and then we're just going to substitute the end, the 3, and the start, the 1. So that is 3 cubed over 3 minus 3 squared plus 4 times 3 minus 1 cubed over 3 minus 1 squared plus 4 times 1, which gives us 9 minus 9 plus 12 minus 1/3 minus 1 plus 4, so that's plus 3, which gives us an area of 8.6672 dp. Number 2. Instead of being given an equation, we're just been given a general picture, and we're told that the integral between 0 and 5 of this function shown is 7. We are then told to calculate this function x plus 2 between 0 and 5. So I think it's easiest first to just sort of visualize what's going on. I'm just going to copy this down, but act with the plus 2. So a plus 2 to a function will just raise it vertically by 2. So everything now is gone up by 2. So we're going to start here. It then goes down. So it was at about 2.5 here. So now it's going to be at 4.5. course, this doesn't have to be perfect. So that's the function now being raised by 2. There's our 5, and here's our 0. The original x-axis, I'm also going to draw that in. That would have been there. So now we know that this area here, that is still 7, but we've got a rectangle underneath. Well, the height of this rectangle is 2, and the base is 5, which is just our upper minus our lower limit, which means that area inside 2 times 5 is 10, which means the total will be 10 plus the old one, 7, is 17. Now, when you're calculating an area and a definite integral where the entire question is above the x-axis, they are exactly the same thing. However, when you're dealing with questions where part of the area you're trying to find is below the x-axis, we have to really understand the difference between what an area is and what an integral actually does. The main difference between an area and an integral is that the integral calculates the signed area. What that means is that any area underneath the x-axis will be a negative, and any area above the x-axis will be a positive. So the integral above x-axis equals positive, and the integral below x-axis equals negative. However, the actual area itself, an area is only a positive quantity, and so when you're working this out, you've got to realize that anything below the x-axis still has a positive area. And so if you're asked in this question to find the area between 0 and 11, well, the area between 0 and 5 is given it as below the x-axis, so the definite integral would be negative 4, but the actual area is 4, and so the area in this case will be just the 4 plus 7 equals 11. However, if you're asked to find the integral between 0 and 11, then you've got to take into account the fact that the first bit is negative, and so this will give negative 4 plus 7, which is 3. And so if you're asked to calculate the area, you have to be very careful, and you have to split the question where the above the x-axis part is and where below the x-axis is. So if you wanted to find the area in this question, you would split it into area 1 is the integral between 0 and 5 of f of x, and area 2 is the integral between 5 and 11 of f of x. Now the first area will give you negative 4, and the second area will give you 7. You've then got to realize that the first area actually is 4, and the negative 4 just tells you that you're below the x-axis, and so therefore you need to make the area 1 positive before adding them together. If you go straight across, the definite integral will sort of start to cancel part of the areas, and you'll get an inaccurate answer. As an example of this, calculate the area between x equals negative 2 and x equals 2 of the function e to the power of x minus 2. We can see that there is a part of the function that is below the x-axis, which will give us a negative area, and a part that's above the x-axis, which will give us a positive area. Now we don't know where it swaps over, so we need to calculate the x-intercept, which is when y equals 0. So firstly, 0 equals e to the power of x minus 2. Bring the 2 over and take the natural log of both sides. X will equal ln 2. So this value here is ln 2. That means that we have our first area, which is the integral between -2 and ln 2 of e to the power of x minus 2, and the second area, which is ln 2 to positive 2 of e to the power of x minus 2. A1 will give us a negative value because it's below the x-axis. We're then going to make it positive, and A2 will just give us a positive value. So A1, well, that will give us e to the power of x minus 2x between ln 2 and -2, which is e to the power of ln 2 minus 2 ln 2 minus e to the power of -2 minus 2 times -2. That gives us -3.5216. The second area is, well, the integration is the same between 2 and ln 2. That gives us e to the power of 2 minus 2 times 2 minus e to the power of ln 2 minus 2 ln 2. That gives us 2.7754, which means our total area is the positive version of -3.52, so just 3.5216 plus 2.7754, or 6.297. Now if we had just gone straight across and done integral between -2 and 2 of e to the power of x minus 2, just for comparison, that would have given us e to the power of x minus 2x between 2 and -2, which when you work that out in your calculator, you get e to the power of 2 minus 2 times 2 minus e to the power of -2 minus 2 times -2, or -0.746, and that is exactly equal to the original A1 but still negative plus A2. The key thing is being very careful when things are below and when things are above the x-axis. Last question, we have the curve y equals sine x, and we're firstly asked to calculate the integral between -2 pi and 2 pi of sine x. Now the integral, very different to the area. Integral takes into account the negatives. In this case we have 4 identical sections due to the symmetry of the sine curve, and so I know that when I add these together I'm going to get a positive, a negative, a positive, and a negative, which is all going to give just 0. So no real integration required. B, calculate the total area. Well, since they're all the same, I'm just going to find the area of 1 and times it by 4. So let's just choose the first one between 0 and pi. I think that's the easiest one. We're going to, area equals 4 times the integral between 0 and pi of sine x, which gives us 4 times sine integrates to negative cos, which gives us 4 times negative cos pi minus negative cos 0, which gives us 4 times, that works out to be 2, or 8 units squared. So when you're doing these questions, look for symmetry. That can speed things up. If you can't, be very careful about where areas are below and above the x-axis. And also, make sure when you're doing a question, if it asks for the area or if it just asks for the definite integral. Those two are two different types of questions and require slightly different working.